Hello everyone, good morning. Yes, happy Saraswati Puja, happy Basant Panchami to everyone. I'm audible, right?
Audible, sir.
Yes, audible.
We'll wait for a few more minutes, then we'll continue. Okay. Okay, so I guess we can start now. So first we'll be discussing one question from practice assignment, week 6. Then you can ask your doubt, okay? From week 5 or week 6. Okay, so do you have any other doubt in week 6 in activity or practice assignment question? Yes, anyone? Okay. Okay, so how many of you have solved the week 6 practice assignment question? Please raise your hand. Okay, only one people. Okay. Okay, so let us take one question. We'll discuss that. So is my screen is visible?
Yes, sir.
So this is question number 10, week 6 practice assignment question. Okay. Okay, so we have given the relation R and these are the set of functional dependencies. And we need to decompose it into BCNF. Okay. Okay. So anyone would like to volunteer how to decompose this relation R into BCNF? Yes, anyone? So first we have to check whether this relation R is in 1NF or not. Is it in 1NF?
Yes, sir, it is in 1NF.
Why?
Because it has only atomic values.
Yes, they have mentioned that the domains of all the attributes consist of atomic values. So it is in 1NF. Now let us check for 2NF. What is the condition for 2NF?
There should not be any partial dependence.
Yeah, no partial dependency. Right. And here for 1NF, it should be atomic values, right? Yeah. Then how to check partial dependency?
First, we have to find the candidate keys.
Yes. So what will be the candidate key here? DEF, okay, how to find the candidate key? Yes, anyone?
We take the attribute which is not in the right hand side, sir. RHS.
Yeah, which is not present on the right hand side of any functional dependency. Yeah. So if all the attributes are present on the right hand side of functional dependency, then we need to take the closure of each and every attribute, then try to take the closure of the combine of other attributes like AB, AC.
The
AB,
traditional way is something.
Sorry, yeah, just traditional way. Yeah.
Okay.
So in this case, we have AB is not present, right? So let us take the closure of AB. AB is okay. Let us take the closure of AB. So from A, I will get D. From D, I will get EF. Okay, so will I get no? So I am not getting all the attributes present in the relation R. So AB is not a candidate key, but AB must be a part of candidate key, right? So now we have to take all the possible combination. Let us check for ABC, ABD, ABE, ABF, ABG, and ABH. Okay. Now let us take the closure of ABC here. ABC, from A I will get D, from D I will get EF. Right. So this is not a candidate key. We are not getting all the attributes right now. ABD. So it is ABD, EF. Here also we are not getting all the attributes. Then let us check for ABE, A, B, E. From A I will get D, from D I will get E, F. So this is not a relation R. Then let us take closure of A, B, F. Okay. A, B, F. From A I will get D, and from D I will get E, F. So still H and G we are not got. So it is not equal to relation R, right? So this is also not a candidate key. Now let us take the closure of A, B, G. Now A, B, G. From A, B I will get D. From D I will get E, F. And from from G I will get H. And from B and H, from this functional dependency I will get C. G is already here, C. So this is equal to relation R. So ABG is my candidate key. Okay. Now let us take the other combination, that is ABH. Here also ABH. From A I will get D. From D I will get EF. And from BH I will get CG. It is G. Yes. So this is also candidate key, right? So ABG and ABH are my candidate key. Okay. So these two are the candidate key. And what are the prime attributes here? Prime attributes A, B, G, and H, right? So A, B, G, and A, B, H are my candidate key. A, B, G, H are my prime attribute, and remaining are my non-prime attribute. Now this relation R is in 2NF or not? How to check that? Sorry. Yes, anyone? When we can say that there is a partial dependency, so suppose there is functional dependency, X determine A, and X is a subset of candidate key, and A is a non-prime attribute. Okay. Now let us check this functional dependency, whether A is a subset of candidate key. Yes, it is. Is it non-prime attribute? Yes. So this functional dependency is not holding true here. Means this is a partial dependency. So our relation R is not in 2NF. Okay. For this functional dependency. Now let us check for this functional dependency. D is also subset of candidate key. EF is a non-prime attribute. So this is also partial dependency. Now BH determines CG. So BH is also a subset of candidate key. CG is also non-prime attribute. So this functional dependency is also partial dependency. Same for this. No, this is not. Both are prime attribute.
How is D determining if partial dependence?
D is okay. D is not a subset of candidate key. Sorry. So D determine F is not a partial dependency, right? We have A determine D and BH determine CG. Right? These two are the partial dependency. Yes. Sorry. Now, in order to make this into NF, we need to remove this partial dependency, right? How to remove this to partial dependency? Now we need to decompose this relation R such that it must be in 2NF. How to remove this partial dependency?
We take the union of LHS and RHS. That will be a relation.
Union of LHS and RHS means AD, right?
Yes, sir, AD.
Okay, then
we remove D from the original relation R.
Okay, so this one be R1, and you said R2 will be, we have to remove D, right?
Yes, sir. A, B,
Rest of
C,
the attribute.
E, F, G, H.
C, E, F, G, H. Okay.
Now again we see for R2 and we have a partial dependency over there.
BH determines CG.
CG, yes. Again, we do the same thing.
Again, we do the same thing. Okay. Now here, R1 to say R2 1 to 3. And here, remaining attribute, right?
Yes, sir.
So our decomposition must be lossless and dependency preserving also. Okay. What should be R2 to?
AB,
AB,
EF, H.
EF,
H.
H. Why you have considered B only here? Why not H? Why not C? Why not G?
Sir, over here we are removing CG, which is in RHS.
Okay, so if we take the intersection of these two, we'll get BH, and from BH we can determine CG, right?
Yes, sir. Yeah, it is a lossless.
The lossless decomposition. But it is a decomposing or like a dependency preserving or not? Now check this decomposition only, R1 and R2. Where it is? Yeah, here. R1 and R2.
Yes, sir. We don't get that determining EF.
Determining EF here, right?
Yes, sir. We don't get that.
So this is not a correct way to do that. So what we have to do is till 3 and F, our decomposition must be lossless and dependency preserving, right? We can do that. Now, what you have taken the union of left hand side and right hand side. So see, there is a partial dependency, right? So you need to take the closure of left hand side here. So what is the closure of left hand side? A plus. From A, I will get D, and from D, I will get EF, right? ADEF.
Yes, sir.
Yeah. So I can take this ADEF as a relation 1, right? R1. Because here this issue with the partial dependency will get resolved, A determine D, and also this dependency will get preserved, right? If you take the closure of A, if I take the closure of A, now same for BH also. Let us take the closure of BH. We'll get BHCG, and from G, H. So it is already H. So I will make this relation as R2. Okay. So now my problem of partial dependency get resolved. Okay. So you have decomposed this relation R into R1, say A, D, E, F, then R2, say B, H, C, G. Whether this decomposition is lossless or lossy? A, B, C, D, E, F, G, H. Okay, if I take the intersection, so it is lossy, right? So I need to add one more relation R3. So what will be the relation? The last session we have discussed this. What will be the relation? R?
AD, sir.
ADE. Why?
AD, that's it.
AD. Why is it so?
Okay, we can't take it.
See, by decomposing this relation into R1 and R2, our problem with the partial dependency gets resolved. Okay, but we need to decompose this in the lossless decomposition, right? So we need to add R3 here. So what will be the attribute of R3? In the last session, we have discussed this. If you are not getting the lossless decomposition, here you can see we have two candidate key, right? So can I take candidate key ABH here? Then check whether this relation R is in 2NF or not. Sorry, lossless or not. If I take R1, say R2, there is no common attribute. So let us take R1 and R3. So I will get A, right? Common. From A, I can determine R1. So yeah, so now let us take R13 such that R1 union R3. So that will be A, D, E, F, and B, H. Now let us take the intersection of R13 and R2. What is the common attribute here? BH, right? BH. Now if I take the closure of BH, I am getting R2, right? From this functional dependency, BH determines CG. So my this decomposition is lossless decomposition, right? Just anyone, any question, any doubt?
Sir, we can take the third relation as A, B, G also, na?
ABG also, yes.
Yes, means one of the prime attribute we have to take. Yes. So
Prime
that
attribute, candidate key, right?
candidate key, that is ABG and ABH, one of the. Okay, sir.
Yeah. You can take G also, right?
Sir,
Till now you understood, right?
ABG.
Yes.
How can we take ABG? Will that be lossless?
Instead of this R3, we will take R3 as ABG. Now let us check. So here A is the common attribute. So R1 intersection A will give R1. Now union will be A, D, E, F, and B, G, right? Instead of H, it will be G. Now there is a common, is there any common between R13 and R2? R13 and R2. It's R13 and R2. Only B is a common attribute, right? So from B, we cannot determine anything. Yes, yes. So it will be a lossy decomposition. So we need to take this ABH only.
Between R13 and R2, we have BG, sir, common at
R13 and
R2.
R2. BG. Okay, BG is there. Okay, BG. Now let us take the closure of BG. So from G, I can get H, yes, yes. And from BH, I can get CG. Right? So I will get my relation R2 here. BH, CG, right? BH, CG. Yes, you can take AB, G also.
Okay, sir. Now it's clear.
Yeah. So if we make one candidate key as a relation, so like in this case, we are taking ABG and ABH. So is this relation like R3 is in 2NF, 3NF, and BCNF also, right? Because ABC and ABG are the candidate key here. So it is in 3NF as well as BCNF. Can we say that? Or do we need to check the dependency here?
We can say it, sir, because it can determine the relation itself.
Okay, we'll see that. Yeah. Okay, so till now you understood, right? I have taken ABH or ABG here. Okay, so we have decomposed this relation R into R1, R2, and R3. Okay. Now, this all the three relations are in 2NF. Okay, so this condition is satisfied. Now let us check for 3NF. And what is the condition for 3NF? There should be no transitive dependency, right? Hello? Yes, am I audible?
Yes,
Yes,
sir.
sir.
How to check whether this relation R1, R2, and R3 is in 3NF or not? What is the condition for 3NF?
Sir, can you do like, I mean, all functional dependency should be a super key thing. The left hand side should be a super key.
For that BCNF, we can say that if whatever the function dependency is applicable for R1, that left hand side must be a super key for BCNF. But in the 3NF, there is one more condition, right?
Right side should be part of candidate key.
Yeah, right hand side should be a part of candidate key. BCNF is more stricter than 3NF. Okay, so let us check first for whether this decomposed relation are in 3NF or not. So what are the function dependencies applicable to R1 here?
A determine D,
and D
D
determine
determine
E.
E.
So what is the candidate key here? A,
A.
right? Now this A will satisfy my 3NF condition because this is a super key, right? Left hand side. Whether this will satisfy my 3NF condition? Because right hand side is not a part of candidate key, right? And left hand side is not a super key also.
Yes,
So
sir.
this will violate my 3NF condition, right? Hello?
Yes, sir. Yes.
Yes, sir. It is validating.
Yeah. Now check for this R2. So for R2, BH determines CG and G determine H is the applicable function dependency. Now this, what is the candidate key here?
BH.
BH, right? BH is a candidate key. Let us take closure of B. We will not get anything. Single will not determine. G will also not determine. If we take BH, okay, so BH is one of the candidate key. BG is a candidate key here. BG is also candidate key, right?
Yes, sir.
BG is also a candidate key. Okay, so BH and sorry, BG are the candidate key. Now let us check for 3NF condition. So BH is a super key, right? So this will satisfy my 3NF condition. And what about this?
H is a part of candidate key. So
Right side is a part of candidate key. H.
Right hand side is a part of candidate key. And what about G? G is
not a super key, so you can say anything.
G is not a super key. So one more condition is applicable here, that it should be there should not be any transitive dependency here. Is there any transitive dependency here? Yes, anyone? Okay, we'll see that. So BH determines CG. So this is satisfying 3NF condition, right? G determine H. It will also satisfy 3NF condition. So this R2 is in 3NF. Can you say that? R3 is already in 3NF. R12, we need to decompose this. What is transitive dependency? If non-prime attribute determine another non-prime attribute, then we can say it is transitive dependency. But here G is a prime attribute, right? So this R2 is in 3NF, but this R1 is not in 3NF. So we need to decompose this. Okay. So how to decompose this? Yes, anyone? Now here you need to take the functional dependency like R11, sorry, R12 AD. Because what is the condition for 3NF? Left hand side must be a super key or right hand side must be a part of candidate key, right? So if I decompose this R1 into R12 AD and R13 as DEF. Now whether this R12 and R13 is in 3NF or not. And if I take the intersection of this, I will get D, and from D I can get DEF. So R13 and R12 is a lossless decomposition and dependency preserving also. So is this in 3NF or not? These two, R12 and R13?
Yes, sir.
Yes. So our 3NF decomposition is, I'm rewriting as R1 AD, R2 DEF, R3 BHCG, and R4 ABH. So these are in 3NF. Now we have to find the BCNF. Okay, so what is the condition for BCNF? Left hand side must be a super key, right? Now here A determine D. A is a super key for this relation R1.
Yes,
Yes,
sir.
it is. So it is in BCNF. D determine EF. This is also in BCNF. And here
BH determines CG.
BH determines CG and G determine H. Two functional dependencies applicable to this relation R3. Now this will satisfy my BCNF condition. But what about this? Is G is the super key?
No, sir.
No. So means this relation R3 is not in BCNF. So again we need to decompose this relation R3. Okay. So you understood this, right? I'll erase this, okay?
Yes.
Okay. Okay, so we have R3 as BHCG. Now we need to decompose this into BCNF. So what is the condition for BCNF? Our left hand side must be super key. So can I make it as BHCG and GH? R31 and R32. Now it will satisfy my BCNF condition. Oh, sorry.
R31 is not
We cannot-
satisfied. No, it is the same relation.
Yeah, we cannot take this. Okay. So we have, because this function dependency is not satisfying our BCNF condition, right? So we make it as a one table, that is R3 to GH. Now this will satisfy my BCNF condition. Now what about another decomposed relation, that is R31? What it should be?
So we can take BHC.
BHC.
C.
Why not BCG? Because anyway BC we have to take, right? For a lossless decomposition. See, R1 union R2 must be R, na? So GH is there. In order to get that, BC must be part of R13, right? But along with the BC, we need to take H and G also in order to get a decomposed relation, right? So BCH or BCG, which one we have to consider?
BCH. Because GH is already there in R3. R32.
Yeah, but why not BCG? Okay, let us take the first BCH, okay? Yeah. So what is the function dependency applicable to this BH?
BH determines C.
BH determine
C.
C. Okay. then yes, okay, BH determines C. And we have BH determine G. Okay, so we can write it as BH determines G or BH determine G. If we take R31 as BCG, then sorry,
We don't have any functional dependencies, sir. We can tell BCGR in our composite key.
okay. So
Dependence is not
let's
with-
see that. Okay, so you take BCH, right? Now, what is the common attribute between R31 and R32?
H.
H. From H, are we getting the R1, R31 or R32?
No, sir.
No, sir.
It is lossy decomposition, right?
Yes, sir.
So can we take this BCH?
No.
No.
BC.
Now let us take BCG. BCG. Now, if we take the common intersection between R31 and R32, G is the common attribute, and from G we can determine H, right?
So R32 is determined. Yeah.
Yeah. So this is a lossless decomposition. But what is the candidate key here? Whether this decomposed relation is in BCNF or not? We need to check this also, no? Because this is BCNF. Okay. What about this R31? What is the candidate key here?
BCG is itself a candidate.
It will determine itself.
Yeah.
If I take the so if I take the closure of B, I cannot get anything. If I take the closure of BC, then no.
We can take BG. BG will
If I take the
determine.
closure of BG, then can I get from G determine H?
And from BH we can get CG.
H. Yeah. So from BGH and from BH we can get CG. Means we can say that BG we can get CG from C, right? From this closure, we can say that, right? BG determines C.
Yeah. So
So
BG.
BG is a candidate key here. Anyone? Any issue?
Sir, is that in 2NF, if we have any partial dependency, we take the closure of LHS?
If we have any partial dependency, then we take the closure of left hand side. Yes. Then we decompose that relation. Consider that relation. Yeah. Here we have done that, right? Yes.
Okay. Only for 2NF we take the closure, right?
No, for 3NF also we can take. But what are the applicable function dependencies are there? Like in this case, R2 we have taken the closure of BH and G, right?
Yes, sir. Okay.
Okay, so we cannot take BHC, right? So BCG is my fourth relation, fourth or fifth relation, right? Now R1, 3, okay.
The dependency is not preserved here, right?
Dependency is not preserved, yes. Till 3NF, we have preserved the dependency, but in this case, dependency is not preserved, yes, right? So that is BCG. So now my decomposed relation will be R1 AD, R2 DEF, R3 BCG, R4 GH, and R5, that is candidate key ABH. Right? So my correct option will be option 3 here.
C.
Yeah, option C. So what is the main application of this normalizing decomposition? We should able to decompose this relation whole R, right? because we need to remove the redundancy which is present in the relation R. So for that purpose, we are doing the normalization and decomposing the relation. So this is the way of doing the relation, decomposing the relation R into BCNF. Okay. You can solve this question by just going to the options also, but that is not the correct way. Okay. By doing that, we will not understand anything. So if we follow this approach, we'll be able to like decompose the relation and understand the concept easily. Okay. So any question, any doubt in this? Yes, anyone? So what is the condition for first NF? For one NF, there should be atomic values. For 2NF, no partial dependency. For 3NF, no transitive dependency. And for BCNF, left hand side must be super key, or it positively determine the left hand side, right? And for 4NF, there should be no multi-value dependency. Okay, so please remember this thing. If the relation is in BCNF, it means it is in 3NF, 2NF, and 1NF also, right? Okay, so any other question? Any other doubt in this decomposition normalization thing? For like 4NF, we have solved one example in the practice assignment in the last session only. You can go through that example.
Sir, could you please release more problems to practice for these normal forms?
In the slide, there are many problems. No? You can check that. You can check the slides also. I think there are many practice questions are there. Yes, you can refer to slide number 27.29. There are 4 relations. Okay, we have decomposed that relation into BCNF. You can practice those questions. You can try that question. If you have any issue, you can post it on the discourse. Slide number 27.29. Yeah. Okay. Any other question? Any other doubt in practice assignment, graded assignment? Not graded, activity question. In week 5, any doubt? Because after SQL part, this week 5 and week 6 is most important concept in DBMS.
So, all the concepts are clear, but we need to practice them. That's it.
Yes, yes. So whenever you get such a question in activity or in graded or practice, please try to follow this approach, like starting from 1NF to BCNF. If you go through the options, you will get the right answer, but you will not able to understand the concept. Right?
It will be objective approach for exams.
That will be objective approach. Yeah. Any other doubt? Any other question? Okay, so based on same concept, question number 8 is there. Yes, so most of the question can be solved. Yes. Okay. Any doubt from week 5?
Sir, I have one doubt.
Yes.
Sir, whenever it is asked in the question to like find the total number of super keys, and so we start with determining the candidate key and check all the possible combinations, right?
Yes, first you need to find out the candidate key, then you need to find out the possible combinations. Yeah.
So what if we in a relation we have like more than 4, 5, 6 attributes, and the candidate key only forms like candidate key will be of 2, 3 attributes. So how can we like combine them and like reduce the number of common super keys? Is there any procedure or something like?
Yes, you can follow.
Sir, may I?
Yes, please.
Okay. Okay, let me show you. Okay. Is it visible?
Yes, sir.
You are talking about, suppose there is this is a number of this is a relational schema, right? And you have, suppose you have the candidate key A, B, A, C, right? This is, you're talking about this, right?
Yes, sir.
So how to find, first, if consider this one as a candidate key, right? And after that, the number of super keys, remaining numbers of attribute, 2 to the power remaining numbers of attribute, that is 2 to the power 3, 8. Similar way, you have to find the numbers of super key for this. That is also 2 to the power 3, 8. But here you have to see there is one combination is also there. You have to take care of this one. This is repeated on this one, this also, and this also, right? This particular combination. So you have to take as this one, and after that's the numbers of super key possible. That is 2 to the power 2. And you have to minus, because this is a sum of in both the cases. So first so it is similar to that union theory, that one, right?
Okay, P of A plus P of B minus P of A intersection B.
Yeah. So this one is 8 plus 8 minus 4, and that is 12, right? In this way you have to check, right?
So we have to consider the common attributes from the candidate keys and check out the possible combination and reduce from the total number.
Yeah.
Okay, sir. Thank you.
Thank you.
So did you understand why we have taken 2 to the power? Because the combination, right?
Because this is occurring in the like candidate keys, so this will also like these will be the common one in total.
Yeah, let me
It will
explain
repeat it.
if you not get that particular part also. So I already explained in the week 2, I think, that one. So if A, B, C, this is A is the candidate key, right?
Okay.
A is the candidate key. So suppose you have to take this particular value, means this attribute, then the possible combination is this is empty set also, empty set possible, power set you have to find the power set, and
Include
so B also, and C also,
and
and
both
here A is there, right? And AB, right? This is possible.
BC, sir.
Yeah. This is right.
Yes,
So
sir.
this is the simple that power set formula of the power set, 2 to the power numbers of attribute,
Yeah, 2 raised to power 4.
2 to the power.
2 raised to power 2 is 4.
Yeah. Okay. Right. I hope it is clear to you how to find it.
Yes, sir, it
No.
is.
Okay. Any other doubt regarding week 5 and week 6 content?
Okay. So any doubt in multi-order dependency? Any week 6 content, anything? Okay, you can try out few examples which is there in the slides for the state of decomposition. Okay, you can try out, you can post it on discourse, or in the next week also we can discuss those questions, because next week is mostly the theoretical part is there. Okay, so
Sir,
Yes.
sir, can you tell how can we remove multi-value dependency from a relation, sir?
For multi-value dependency from a relation. Okay.
Yes, sir. If we want a relation to be in 4NF, we should not have multi-value dependency, right?
Right.
How to
Okay.
determine it?
Let us take any question. Okay. Yeah. So in the last session, I have taken question number 9, which is based on MVD. So how to remove that MVD? Okay. So let us take question number 6 today. Okay. You see that. Is my screen is visible?
Yes, sir.
Okay. Okay. So we have the given relation intern and okay. So here it is condition: an intern can work in several projects and can have several hobbies. However, it maintains the functional dependency intern determine intern name. Okay, so there is only one functional dependency, right? Now we need to find out the appropriate 4NF decomposition for this. So what is 4NF means? There should not be any multi-valued dependency, right?
Yes, sir.
Okay, so but for that, the relation must be in BCNF also, right? If it is in BCNF, then only we can decompose it. That first it should be in BCNF, and there should be first condition is it should be in BCNF, and there should no multi-valued dependency. So these two are the conditions for 4NF. Now whether this relation intern is in BCNF or not, we have this functional dependency here.
It is not in BCNF.
Not in BCNF because this is not a super, right? Now first we need to decompose this relation into BCNF. So how to do that? They simply take the closure of internal underscore code. It will give us internal underscore code and this name. So we can make it as one relation. Intern underscore code and intern underscore name. And what will be my second relation R2 here? It should be lossless decomposition, right? So
Intern code project hobby.
Intern code project hobby, yes. So intern code project hobby. Okay, so now this decomposition is lossless. Internal code is a common attribute. And from this, we can determine R1. Okay, so this is in BCNF R1 and R2 is in BCNF or not? Yes, anyone?
Yes,
What is the key here?
all three
All the three attributes, right? Because there is no functional dependency applicable to R2, right?
Yeah.
So all the three attributes are the key here. Okay, so R2 is also in BCNF. So this is also in BCNF. Now we'll have to check for means we need to decompose it into 4NF. So we need to remove the multi-value dependency. So what is the multi-value dependency here? What is the meaning of this? Intern means intern. What is the intern code can multi-determine several projects. And same, intern underscore code can have several hobbies. So hobbies, right? So these two are the multivariate dependency. Now we need to remove this multivariate dependency in order to decompose it into 4NF, right? So what are the multi-dependency applicable to this R1?
None of them are there.
Also, then R2, for R2,
Both
yes,
of them.
both applicable. Now how to decompose this? How to remove this multivariate dependency? Simply we can take one relation R1, R2, like sorry, R12 such that intern code project, and then R13 as intern underscore code hobbies. I need to solve my problem, right?
Sir, but the multi-value dependency is carried to that, no, sir?
So what is the definition of multi-value dependency here? See, if there are three attributes A, B, C, and this both attribute B and C are independent of each other, but it depends on the third attribute, that is A, then we can say it is a multi-value attribute. For multi-value attribute, we should have at least three attributes in the relation. At least three attributes in the relation. So if we make the relation intern underscore code and project, so that we have only two attributes, right? So that is not a multi-value dependency here applicable to that. If we decompose this R2 into intern underscore code and projects, and here intern underscore code hobbies. Okay. There are only two attributes, right? For multi-value dependency to hold true, there must be at least three attributes. Then only we can say this, that there is a multi-value dependency exists in the relation. But here we have only two attributes. There is no multi-value dependency in this. So the correct answer will be C, not C, D. It's R1, R2, and R3. Okay.
Okay, sir. Sir, R1 is in 4NF because item code is a super key. Can we tell like that?
There is no multi-value dependency applicable to this, right?
Yes, sir. I understood that point. Can we tell like that?
In term, no. For 4NF.
Yes, sir.
Yeah, we can say that because it is in BCNF also, and there is no multi-value dependency. So these two conditions must be satisfied for 4NF.
Okay, sir.
Okay, so there is no any question. So we'll take few questions on peer deck platform. Okay. Yes, Subhendu.
Yeah, let me give 1 minute. Yeah, my screen is visible, right? Hello.
Yes, Subin, visible. Yeah.
Okay.
Yes.
Okay.
Add-ons.
Okay. Link in the description. You can join using the following code that appear in your screen. So, Subendu, can you share the joining code?
Subin, you have stopped sharing, not sharing that. Can you present the session again? Okay, you are on another tab. Okay, fine.
Okay, 10 students joined, 12 students joined. Okay, so you have to directly decompose into third normal form. You have to tell how many tables are required and their attribute names, like R1 decomposition and the attributes names, like that you have to tell in the chat box. There is a relation R X, Y, Z, W, and the functional dependencies are X determine Y, Z determine W, and you have to decompose directly into 3NF, and you have to tell decomposed like R1 and that attributes name like X and Y, like that you have to tell.
sorry. Yes, how many students have responded? 4 responses, 5 responses. Okay.
Sir, we have to decompose this in 3NF, right?
Yeah, you have to decompose into 3NF, and you have to tell also attribute them like R1 and the attribute name, R2 and the attribute name, like this.
Okay, sir.
You will wait 3 or 4 minutes so that more responses will get.
Please try everyone. Okay, you can expect this type of question.
Okay, I think Sugandhu, we can discuss this question.
Okay, we get only 6 responses. Okay. 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 So anyone want to tell what is the candidate key?
Sir, XZ.
Okay. Yeah. XY, ZW, and XZ. The correct option. Yeah. So we have written R1 XY and R2 ZW. Can you say? Okay. Can you say? It will be lossless or lossy decomposition?
It will be lossy, sir.
So it will extra table record, right?
Yes, sir.
Okay. 3 table XY, ZW, and X. Yeah. So those who have give right answer, can you explain what is your approach?
Yes, sir, I can explain.
Okay, please explain.
So the sir, like according to the given relations, the XZ will be the candidate key. So there is a partial dependency X to Y and Z to W.
Yes.
So we have to decompose them. So we'll decompose them in X, Y, and Z, W, and to preserve to do the lossless join, we will also consider XZ as a table.
Yes. Yes. Okay. Yeah. Good. R1, XY, ZW, and XZ. Okay. Yeah. So those who have written R1, we have written around xy and xzw. Can you explain? It is in 2NF. We have gave the answer. Okay, no issue. Okay.
Okay,
So
Subhendu, you can explain that why it is wrong, that particular question. Yeah,
okay,
that particular solution.
okay. See, what is the candidate key?
X and Z.
Yeah, so xz is the candidate key and x determines that there is a partial dependency. So it is not in 3NF, in R2 table. See. Okay. Now I will show you how to decompose third normal form directly. So let me stop my screen. Let me share. Okay. Okay. So I will show how to decompose a relation directly into 3NF. So okay. So first you have to mm, first you have to write canonical cover of F of functional dependency. Then for each relation, for each functional dependency, you have to make one relation. And the last, you have to see if there is a candidate key present in Ri. If there is if there is not does not present in candidate key in Ri, then you have to make another relation candidate key. Like you have solved the example like x determine y, z determine w. What is the candidate key? X z. So first you have to make for x y you have to make one relation x y for each for each functional dependency. Then you have to make another relation zw, and you have to see xz is present in relations Ri. Xz is present.
No, sir, it's not present in both.
Both, so you have to make one more relation xz. So you can approach this way directly. Okay. Then next, okay, let me share my PR deck. Okay. Okay, next question. You have to decompose into directly into 3NF, and you have to tell relation and the attribute name. We'll wait 5 minutes so that everyone can responses. Okay, we got 9 responses, so we can discuss. So R1, what are the functional dependencies? A, B, C, D, B, E. Okay. Okay. Whoever writes this option, can you explain? Whoever gave the first option, can you explain why this is right? Okay, no issue. Okay, whoever gave this answers, can you explain why this is right?
Sir, AB from AB we can determine A, B, C, D, E. So AB is the key,
Yes.
candidate key. So I've kept that in one table, and C, D, E cannot determine anything, but they can be determined by R1. So their union will be the parent functional dependency.
But this is a lossless zone.
Okay, this is lossless also, and R to CD are not a means super key or the candidate key, right?
Yeah.
Okay.
So okay. Subhendu, can you correct that question?
Yeah. So in the next option, there is A, B, C, D, and R to give right answer. So can you explain why this is right?
Yes, sir. I give this answer.
Yes. Can you explain?
Yes, sir. So in the original relation, AB is the candidate key.
Yes.
Here we can clearly see that B determines E is a partial dependency because B is a prime attribute.
Okay.
So we'll decompose them in two tables. One table will be BE and second will be ABCD.
Okay. Yeah. Thanks. Okay. And this is also right option. This also right option. This also right option. So we have gap. This option. Can you tell why this is right option? Okay, no issue. Okay.
Sir, can you explain why the others are wrong also?
Okay. Okay, Subhendu, can you stop that sharing? I will explain
Okay.
that particular question. Okay. Okay. Is it visible, right?
Yes, sir.
B and the functional dependency you have read. AB to CD and B to E. Can anyone tell what is the candidate key?
Sir, AB.
AB.
AB, and how to calculate that? Hey, here you can check. First, you have to check the right hand side. So E is present in the right hand side. CD is also present in the right hand side. So in the candidate, AB is required. So you cannot derive by any of the functional dependency, right? So finds the AB closer. That is AB and after that AB2 you get the CD, right? And B2 gets the E, right? So by default this functional dependency in first enough, right? So we get this candidate key as the AB, right? So we have to check for the second NF. So what is the condition of the second NF? Can anyone tell?
There should not be any partial dependency.
Yeah, first it have to be first normal form, right? And the second condition is no partial dependency. And what is the partial dependency?
Sir, B determines C and is a partial dependency.
B determined E, right?
Yes, sir.
Because B is a part of candidate key.
Yeah, prime attribute.
Yeah, and that is the proper this is the proper subset of the candidate key, right? B is the proper subset of candidate key. So we not allowed in the second NF, right?
Yes,
So
sir.
this particular violates that's the second normal form. So what we do, we decompose this particular one. So we get this. So we decompose this R to R1, R2 and R1. And R2 what we get? This particular BE. And in this B is a that candidate key or the prime key, primary key. And the second one ABCD, right? ABCD, and these two are the candidate key, right? So now you have to check for the third normal form. And can you say what is the condition for the third normal form? For this one, you get the functional dependency like this for this R2 and the for. So tell me what is that third normal form?
No transitive dependency.
Yeah, first it have to be second normal form. And the second one is no transitive dependency. Right, up to this is clear. So check here. So this is no transitive dependency, and one condition you have to remember is that there are three conditions of the third normal form, that it can be trivial functional dependency. Yeah.
Left hand side should be super key.
Yeah, left hand side super key.
Right hand side should be part of candidate key.
And this all are or means you have to satisfy one of the condition, right? And the right hand side should prime attribute, right?
Yes, sir.
Okay, so let's check for this particular one. Here the functional dependency B to E. Here you can say B is the candidate means primary key, so it is super key, right? It satisfy the condition.
Yes,
okay, in R2 you have to check this particular one. AB is also primary. Yeah, primary key. So left hand side is a primary key, so it is also in third NF, right? So can you tell it is in BCNF or not?
Yes, sir. It is also in BCNF because in both the relations, left hand side is a super key.
And can you tell what is the condition of the BCNF?
Left hand side should be a super key.
Yeah.
And it should be in 3NF.
Yeah. Must be, right?
Yes, sir.
And it should be in third NF. Right. So it is clear to you, right? How we can decompose it into third normal form. It is clear to everyone, right?
Yes, sir.
Yes, sir.
Okay. Okay, Subhendu. So I think you all have gone through that particular extraneous attribute. Can anyone tell what is the extraneous attribute? Anyone in the week 5 contents, there is the one important topic that a canonical cover, how to compute the canonical cover. At least anyone can try. We are not here to judge you.
Excuse me, sir.
Extraneous.
Spurious tuples are called extraneous attributes.
Can you be specific? What is the spurious?
Sir, when we decompose a relation and when we join back to get original relation, then then that time we get extra attributes which was not originally present in the original relation. That is called extraneous attribute or spurious tuples.
And in terms of the functional dependency, can you tell? What is the extraneous attribute in the functional dependency?
Yeah, so sir, if we can remove that particular attribute from the functional dependency, it won't affect the overall functional dependency relation.
Yeah. And suppose in the alpha to beta, there exist some attributes in the alpha you can remove without affecting the original functional dependency. So, right. So can anyone tell how to test in there is extraneous attribute on alpha side or not?
If we remove that attribute, then the closure of alpha minus that extraneous.
Okay, let me write. Suppose you try to compute this A is extraneous attribute in alpha or not, right? So
then
tell me.
I must take alpha minus A closure.
Okay.
Then if the dependencies on with this are preserved, then we will say that A is an extraneous attribute.
Okay, alpha minus A closure contain beta. Then we can say this alpha is an extraneous attribute, right? On the left hand side.
Yeah.
Okay. So let me take an example, right? So can you volunteer how to this, suppose how to compute the B is an extraneous attribute or not in this particular one? So we already discussed about the what is the that step by step. So in that example,
Sir, as A closure is AC, so that A is determining C, so B is an extra attribute.
So for that we have to means that okay. So we have to check for the B is an extraneous attribute here or not, right?
Yes, sir.
So for that, from the alpha means that yeah.
AB we remove B.
Means that
no sir.
B closer, and that is the A closer, right?
Yeah.
So we have to find the A closer. So if here you can see A closer is C is present.
AC.
right? So we can see this B is an extraneous attribute in alpha, right?
Yes, sir.
So it is clear to everyone.
Sir, actually, I
The
have a
heart.
doubt over here. Sir,
Yeah.
after removing this, for finding the closure, we are not going to consider the second functional dependency from the original functional dependency set.
No. So here you have to compute this particular. You have to you have the functional dependency right now. That is the A to C and AB to C, right? And here you have to find this particular one closure, and that is the A closure. So try to find the A closure. So
Sir,
you get
we have to calculate this A closure from by removing the this AB determines C from the functional dependency set.
no. That is, so you have to remove this one. So you have to, for the left hand side, you have to compute only this particular one. So this is the
Okay, sir,
formula,
okay.
right?
Yeah, if we consider only A, we are not going to get the second. We are not going to use a second functional dependency.
Yeah, exactly. We don't need to use that.
No, that is for the right hand side. This one, for when we have to check the this beta is an A is an extraneous attribute or beta or not, then we have to see that particular thing. So what we come to later that one.
Sir, I am saying that like we have AB here, so we remove B from AB. Then the left one is A only, so we cannot use this AB determines C as well, like because we only have A. We have to calculate the A closure only. So no need to remove this from the functional dependency set.
No, it doesn't affect this particular one. So
Yeah,
suppose.
that's what I'm saying. Yeah.
Yeah, so here we are finding out whether A is extraneous attribute or not. So that's why we take the alpha, then we minus that A, then we take the closure of that, right? So in this case, A, if we take the closure of A, we'll get AC only, AC, right?
Yeah, sir, we understood, sir.
Yeah.
Okay, this is for the left hand side, how to calculate the alpha side, A is an extraneous attribute or not. So how to compute the beta side for that? Can anyone tell?
So sir, for that we will remove the alpha determines beta minus A functional dependency from the
Okay. And let me write your, what is the A beta 1, right?
Yes, sir.
So what is the first step?
Sir, we'll remove this dependency alpha determines beta minus A.
Yeah, this particular one, right? So you want to remove that from the whole functional dependency present in the F, right? F is your means whole functional dependency, right? So from here you want to remove this particular one. So that is this one, right? After that
we'll include the dependency alpha determines beta minus A.
Right. Okay. And second step?
And now we'll calculate the closure of alpha.
Alpha closure, right? And if it contains the beta,
then A is extraneous.
Then we can say A is an extraneous attribute in beta, right? So let's take an example. So A to C and A to CD is there, right? So what is our now? What is F dash? Can you tell?
AC, A determines C.
A determines C, and the second one, this particular for this one.
This is also
Here you have to check for this one, right?
yeah.
So this one is
A determines D.
A determines D, right? So now finds the A closer. A closer, yeah, A closer, right? And you get that A, C, D. Here you can see that the C is present here, and that is beta, right? And we said that if A closer beta contain, then we can say A is an extraneous attribute on that, means that C is an extraneous attribute, this particular one. So we remove it and we get the A to C and A to D, right?
Sir, CD is beta here, no? Not only C.
Which one?
So you
No, we check for this particular one.
Yeah, I got you. We check for C, but CD is beta, right?
Okay, I say okay. I wrongly said. If A closer all A is contained in A is present in beta, right?
Yeah, then
we can say that A is an extraneous attribute, right? So is it clear, everyone? How to find the extraneous attribute on left hand side and the right hand side?
Okay, if we have extraneous attribute in beta, we are going to consider the F dash for the closure.
Yeah.
Okay, sir.
So any other doubt? So everyone, what is F cover 1, F1 cover F2 and F2 equivalent? So can anyone tell what this particular statement means?
like, sir, if we have two
F1 covers F2. Okay. Yeah, tell.
Yeah, so if we can like all the functional dependencies of F2 are in F1, then we see that F1 covers F2.
So let me write what you have said. Suppose this one is F1 and this one is F2, right? So
if all the functional dependencies of F2 are present in F1, or we can determine those functional dependencies from F1, then we can say that F1 covers F2.
Okay, let me write some functional dependency A to C and B to D, right? And so for C, A to CD and B to E to D, right? Can we say that F2 covers F1? So how to calculate that particular one?
Sir, for that we will calculate the closure of A and check.
And using this particular one,
yeah,
we try to find the closure of A, and that is A, C, CD, right? So AC is present. Here you can see AC is present, means this particular function, and try to find this beta B closer using this particular one.
BED.
And so we get the BED, right?
B is
so
present.
Here B is present. So we can say that the F2 covers F1, right?
Yes, sir.
And can we say the opposite one, that
we have to check that.
okay, let me tell me. Okay, F1 covers F2. So we have to find this particular, we already checked that is present, or no, we have to check that.
Yeah.
So what we get? Only AC, right? So CD is not present. Okay. So here you can see the A2, CD is not present, right? D is not present in this particular one. So we cannot say cannot say that F1 F1 cover F2, right? So we no need to check further. Here we get this particular condition is not satisfied. So we can say that F1 not covers F2, right?
Yes.
Okay. So any other doubt?
Yeah, okay. Any other doubt? Just try to solve more practice problems, okay? Just go in the slide also. And we
So
have
this
released.
so
Yes.
this cover thing is the same as a canonical cover, right?
No, that is different thing.
Oh.
Canonical cover is a different thing, right? So
Can you explain that?
canonical cover, right?
Yes.
Okay. So here you can see the F1, okay. F1 and the F2, right? F2 covers F2, F1 covers F2. So canonical cover is canonical cover. Suppose FC we denote as this is the canonical cover, right? For the functional dependency F, this is the original one. So you have given the original functional dependency and you have to find the canonical cover FC, right? And this one is the, so these two are equivalent. What does that mean? FC covers F and F covers, right, FC. So this means these two are equivalent. So there are another condition also for the FC. So it should not contain any extraneous attribute, right? So first condition is okay, not contain any extraneous attribute. So we already discussed about how to remove the extraneous attribute from the functional dependency, right? Who asked that question? Hello.
Yes, sir.
Yeah. So FC must be it not contain any extraneous attribute, right? This is the first condition, and the second condition is that suppose there is all the left hand side should be unique. What does that mean? Suppose there is the present like this A to C and A to D, right? This is present. So left hand side should be unique in FC. And what does that mean? So you have to union this particular one. And after union, you get that B, C, D, right? So this is allowed in the FC, right? And so there should not be any extraneous attribute. So here you can see this all functional dependency are not extraneous attributes, right? You can check that.
Okay, sir.
So, okay. So Any other doubt? So, okay, Piyush. Okay. If any other doubt regarding week 5 and the week 6, otherwise we can wind up. Okay. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, everyone. Have a nice day.
Thank you, sir.